Hello. So this is too important for me to leave to Mr. P. So I'm going to go over with you how to draw the free body diagram and then how to transfer that information from the diagram to a net force equation so we can solve for something. So you've already seen these situations, but let me go through with you what forces are acting and then let's just go from there. So first thing is this block hanging from a string. And so these are the 7 forces that we're most likely to have to deal with. And certainly the gravitational force is almost always going to be present in any free body diagram that we draw. In this case, there's no spring. There is a rope or string, so there's tension. The normal force is one of the more confusing options because the word normal means every day, but here normal means perpendicular, and specifically the force exerted by a surface. So since there is no surface acting on the block, there is no normal force, and so it is absent. There's no friction here because it's not sliding or trying to slide. There's no applied force. And finally, air resistance. This is another confusing one. Air resistance is only relevant if the problem makes it exceedingly clear that it's relevant. Oh, it's just too early in our treatment of mechanics to worry about air most of the time. So since this object is stationary, we're not worried about air moving. So I would say absent. When we draw our free body diagram, we're going to draw a distinct arrow for each force. And so in this case, we have 2 forces, one gravitational force. The gravitational force always points towards the center of the Earth. And make sure when you draw your arrows that they're touching the object or dot that you drew to represent the object. The other force is a tension force straight up, which you can call F sub T or just T. I try to make myself do F sub T so that I don't get it confused with period, which is also a capital T, but sometimes I use tension as T. Okay, so moving on. The net force equations. The first one is always Newton's second law. This is always true. And so it's good to start with it because that's always true. F equals ma. The second equation, actually, make that note. It's always true. The second equation comes from the diagram. And so in this case, we're specifically looking at the y direction. Now, if we have both forces in the x and y, we would have to treat them separately. We get to choose what direction we call positive. So if there's no good reason why not, I'll usually call up positive. And so our second equation here would be tension minus the weight. Now from there, we're going to set them equal, and usually we're going to solve for something. Now here, since my goal is just to introduce this process, I'm not asking you to solve for anything, but I just want you to get used to the process. So now we set them equal. MA equals FT minus FG. So again, the first equation is always true, F equals MA. Second equation comes from diagram. And then once we have those two, we set them equal. And then usually we'll solve for something. All right, moving on. Number 2, a ball is at the top of its flight after being launched from a spring-loaded cannon. We're specifically considering the forces at the top of the flight, so right here. So I purposefully made this a little bit of a trap. Certainly there's a gravitational force, and the word spring does show up in the problem, but that's not acting on the ball anymore. When we draw a free body diagram, we are only concerned with the forces currently acting, not what happened in the past and not what's going to happen in the future. And so we are going to have absent for all of the rest of these because at the top of its flight, none of those things are relevant. It doesn't say anything about the air. It is moving, but since it doesn't say anything about the air, I'm not going to worry about it. So I'm going to choose N for negligible. So it's like technically not 0, but it's close enough I can ignore it. So the only force acting for any object in free fall is the gravitational force. So again, this is the free body diagram for any object in free fall, no matter what the situation. So when we set up our net force equations, first one's always F equals ma. Second one here is Fg. You get to choose what direction to call positive. This is tricky. I guess I'm going to say down is, I'll call up positive. And so I'll say this is negative Fg. So then I can set them equal and say MA equals negative FG. Now, one of the videos you've already seen, or one of the things you've already looked at is the relationship, but what is gravitational force? We know that gravitational force, or weight, is equal to mg, where g is 10 newtons per kilogram. And so we can go a step further in this specific one. So we can say, since ma equals negative fg, that must mean that ma equals negative mg. And so we see the m's cancel out. And so this is something we already knew, but here's why. For an object in free fall, the acceleration is equal to about 10 newtons per kilogram, meters per second squared, which is dimensionally the same. And it's in the downward direction. Now, okay, strictly speaking, it's not 10, right? It's 9.8. So make a note of that. Web of Science is going to want you to use 9.8, but everywhere else, 10 is fine. Okay, moving on. In number 3, now we have this phrase terminal velocity. Terminal velocity specifically is a situation where the acceleration is 0. Terminal meaning final. And so it's not speeding up anymore. We talked about this way back on like the first day of school with dropping like a wiffle ball from the 3rd floor. So we have the weight force, but then canceling that, we have air resistance for the first time. And so and those are the only 2 forces. And so our diagram, again, we'll have FG down. Now, honestly, a lot of times, there's pros and cons to any approach that we take, but a lot of times instead of calling it FG, I'll just label it MG right off the bat. And so that just takes a step out later. Besides the gravitational force downward, we have the air resistance upward. Now, in situations like this, where we know the acceleration is equal to 0, I'm going to set that up right off the bat. And so that way I can use that tool as we move forward. Our second equation from the picture. Let me set them equal. And then we can solve for something. All right, moving on. Sorry, I'm rushing. You can pause the video. Moving on, a block is pushed across a rough table. All right, so certainly a weight force. There's no spring, there's no rope. There is a normal force because we have that table pushing up. It tells us that the table is rough, and so yes, we have friction. And there's this weird disembodied arm, and so there's an applied force. It's moving. So yeah, sure, there's some air resistance. I'm not going to worry about it. So for our free body diagram, we're going to have 4 forces acting. We'll have that weight force straight down. We'll have the normal force straight up. We have the applied force to the right. And we have the friction force to the left. And so here, when we write our net force equations, we have to separate what's happening vertically and horizontally. So in the y direction, we have no acceleration. We have the normal force up and we have the weight down. So 0 equals Fn minus mg. Most of the time, the normal force and the weight are the same size, but certainly not all of the time. We also have forces in the x direction. Now, it doesn't say whether this object is accelerating or not, so I'm going to I can't say that it's equal to 0. The second equation comes from our picture. So then we can set these equal. And again, solve for something. So again, just make sure you see what's happening here. I'm setting up my 2 net force equations. First one's always true. Second one comes from the diagram, setting them equal and solving for something. All right, and number 5, a block slides across a rough table. So the weight and normal force, just like before, in the y direction, What's strange here, though, is even though something must have been pushing it in the past, it's not pushing it anymore. And so there's no applied force. This is confusing. Students usually, not usually, but students sometimes want to have a force in the direction of motion. But the reality is, Newton's first law tells us that no force is needed for an object to be moving. A force is only needed to change an object's motion. So here, the force that's changing the object's motion is the friction force, which opposes the sliding. And so when we draw our diagram, like before we have mg down and Fn up, and like before we have a friction acting to oppose the sliding, but there's nothing acting in the direction of motion. When we set up our net force equations, again, this is identical to the previous one in the y direction. But in the x direction, we only have, well, hold on. We only have the friction force. Now, I find it most intuitive to call the direction of motion the positive direction. So since it's moving to the right and since the friction is to the left, I would have this friction force be negative because then the slowing down has a negative acceleration, and that's what my brain wants it to be. And so this becomes max equals negative ff. Great. All right, last but not least, this crazy one. So here I photoshopped numbers 4 and 1 together because, you know, I'm pretty skilled at Photoshop, as you can see here. But so this block is being held stationary against a rough wall. So the easiest one to start with is certainly the gravitational force. Okay, fine. We also see that hand pushing it, so there's an applied force. It tells us that the wall is rough, and so a friction force is likely important. And finally, because it's being held against the surface, there's a normal force that's present. So we're going to have these 4 forces acting. What's tricky is trying to figure out what goes where. So the easy one is mg. The gravitational force is always straight down. After that, it gets a little weird. So the arm is pushing it into the wall, and let's say it's perfectly horizontal, like so. The normal force, by definition, is perpendicular to the surface that provides it. So that must mean that it is leftward because the wall is vertical, okay? And finally, the reason it doesn't slide down the wall is because the friction prevents that from happening. Friction exists when an object is sliding or when the friction is large enough to prevent sliding from happening, which is what the situation is here. And so that's why the friction force prevents it from sliding. And so therefore it points up against the downward force of gravity. So this object is not accelerating in any direction. And so we can set up our net force equations. Again. Oh, whoops. This is Fn. Sorry, I wrote Fa. That's Fn. When we're doing two-dimensional problems, we usually often need to start by calculating the normal force. So even though we've been starting in the y direction so far, I'm actually going to start in the x direction for this one. It doesn't really matter, you know, we would get there eventually anyway. But just because often a first step is solving for Fn, for reasons we'll cover soon, I'm going to do that. I'm going to set it up that way. So the net force in the x direction is 0. And the net force in the x direction is, I'll call to the right positive, doesn't really matter. And then in the y direction, oh my gosh, it's so All right, so now that we have covered the basics, you're almost ready for numbers. How exciting. But even when you get numbers, please, 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 please start with a free body diagram that has only quantities on it, only labels, no numbers. Then write your two net force equations, again, no numbers. Set it up with the names of the forces or the symbols for the forces. Set them equal, isolate what you're looking for, and then numbers come in at the very bitter end, okay? Stick with the symbols as long as you can. All right. I'll see you later.